Here we are, 6.4 part 1, the FTC, Fundamental Theorem of Calculus. And you know me, in 20 seconds or less, this is basically that the derivative and the integral are inverses. So let's do some little warm-up problems here. This is an indefinite integral, x cubed over 3 plus 3x. That gets a C. Now we have a definite integral, so we take x cubed over 3 plus 3x. We draw our line, -1 to 2, and we compute. So I've got 8 over 3 plus 6 minus, okay, and then I'm going to throw -1 in there, so -1 over 3 minus 3. Not a lot of room here, so I'll do my best, because this won't take much space. 8 over 3 plus 18 over 3 minus -1 over 3 minus 9 over 3 equals what? 26 over 3. That's all going to be a positive 10 over 3. We are looking at 36 over 3, which is 12. Okay, so that's the second one. Let's integrate sine. That's going to go up to negative cosine of x plus c. Looking good. And then our last one is the sine of x, which is going to be the same antiderivative that we'll put our bars there. And we've got negative cosine of pi over 4 minus negative cosine of 0. Okay, so that's negative root 2 over 2 minus 1, and minus a minus 1, I should say. Minus, let me just throw this in here, right there, I guess. That doesn't look so great, but root 2 over 2 plus 1. Really crammed in there, sorry guys. All right, so a little bit of review there, and you know, basically we know the difference between an antiderivative and a definite integral. An antiderivative is a new function, you know, plus c, and a definite integral is it's a number, it's an actual value there. Okay, let's look at number 1. So we would just go here and say, all right, so now, you know, what's different? It's now a variable up here, but, you know, no big deal. We can handle this. So what's the antiderivative for, you know, cosine? That's just going to be sine, differentiates to cosine. So sine of t, and we're going to go from 0 to x. So sine of x minus sine of 0. So we just get sine of x, okay? All right. How about here? This is going to be t to the 1/2. So raise the exponent by 1, multiply by the reciprocal, 2 to x. 2 over 3x to the 3/2 minus 2 times 2 to the 3/2 over 3. I'll just leave it at that. Can't really, you know, square root of 2 is not a perfect square, so we'll just leave it there, I guess, for that one. And then this one is t cubed over 3 from -1 to x, which is x cubed over 3 minus -1 over 3, which is negative x cubed over 3 plus 1 over 3. Okay, so not too exciting going on yet. Each time we get a function here, though, when we integrate f of t with regards to t, our upper bound is x, we get a new function in terms of x, okay? So this, you know, it's written here in t, but this upper bound takes control, if you will. And now we get a new function written in terms of the upper bound, f of x, the antiderivative, plus c here. I wouldn't even really say plus c here. I don't know, because you've got the upper and lower bound. But so I wouldn't even have that C there, like I said, but I'm going to just put it here just for grins for a minute. I mean, basically this does have a, plus 0. This is a constant, and this is a constant. I mean, when you integrate a definite integral, you get the function. But I'm going to leave this plus C here because with the fundamental theorem of calculus, I'll just kind of revisit this here in just a minute. Again, pretty technical, but all right. So we're continuous, always continuous. There exists a function such that, if I have this a to x, so notice I've got this 0, this 2, this -1, okay? And those are all very important because they're what we're subtracting off, okay? And so, we can, if we do, f of x is a function. Now, f of x is now this integral function, okay? It's a definite integral function from a to x. For this definite integral to produce a new function, the integrand is written with a constant lower variable. Okay, so we kind of call it a dummy. And it's not really a dummy variable, I would say. It's just some number, okay? Just some number here. And the upper limit is the variable of the new function. All right. So again, this probably isn't making a whole lot of sense, but it always makes more sense when we look at a problem. So when I do d dx of this integral, okay, these are inverses. You're just going to end up with cosine of x. I mean, that's the big picture here. But we're going to go through the process, and then we're going to discuss why I put this c here. Okay, so let's leave the derivative alone. Let's integrate, right? And so this is going to integrate up to sine of t from 0 to x, okay? And then that's d dx. Here comes the new upper bound variable. And it's asking us, this is, honestly, guys, this is just showing you that derivatives in integrals are inverses, and that's kind of like, duh. All right, so sine of x here. And so if I differentiate here, I'm going to get cos, and you know what, let's actually put in, let's actually address this plus c, plus 0. And so when I differentiate this, I'm going to be right back to where I started, cosine of x. So the fundamental theorem of calculus basically says if I take d dx of an integral, I'm just going to get this itself written in terms of the new variable. So this plus c is going to differentiate to 0, okay? So you don't really need to write it here, but where this is important is to realize this lower bound does not matter what it is, because it's gonna shake out to be a constant, which when you differentiate with FTC is 0 anyway. So it's weird because it's hard in math to say something just really doesn't matter, but if you have a situation such as this, so here we go. If you see the derivative of an integral, look for the upper bound to be the new variable. Don't care, but it needs to be a number, okay? And so, right away, this answer is going to be root x, period. That's what you want to get out of this. So let's go through the process and show that inverse relationship. So this will be t to the 3/2, 2 over 3, from 2 to x. We've done all this up here. We got that 2/3 x, upper bound, minus that 2 to the 3/2 over 3. And sorry, I stole my d dx here. Okay, and so then when I differentiate this piece, the 3/2 will come down, cross cancel. I'll just go over here. Minus 2 over 2. Boom, boom. We are back to x to the 1/2. All right. And when I differentiate, I guess I should, my d dx all of that minus 0, that's just a constant, x to the 1/2, which is as anticipated, root x. All right. Okay, so d dx of a constant, don't care what it is. It's gonna, you do care what it is if it's just the integral, the definite integral. But when the d dx is in front, you don't care because it's gonna differentiate to 0. All right, so you got to watch for the squaring of the square root, right? The exponentiating of the logarithm. And then if we opened this class talking about the fact that, or this semester talking about derivatives and integrals being inverses. This is just showing you, the way. All right, so d dx of 2 cubed over 3 from -1 to x. Okay, d dx of x cubed over 3 minus 1/3. d dx of that, right, is just going to be x squared plus 0. So in other words, if we integrate and then differentiate, we get back to the original function, and it's written in that new variable. Okay, so this suggests that integration and differentiation are inverses of each other. Just like multiplication and division, and addition and subtraction. All right. What's next? All right, so let's do the theorem, the big theorem, the fundamental theorem of calculus, part 1. Continuous, f is continuous. Okay, on AB, x is in between AB, there exists a function, an antiderivative, such that, you have f of x, this upper bound is x, we're going to have f of x here. It'll be written in terms of this new, so you've got this situation, and once all of this is said and done, the antiderivative will be written in terms of this new variable. And then if you go ahead and differentiate that, you're just going to get f of x. All right. So for the following examples, integrate to find g of x, then differentiate to find g prime of x. Remember the hypothesis. The integram must be continuous. Okay, so square root, this is continuous. That's continuous. And as is cosine. So those are both great. All right. So we're going to differentiate to find g prime of x, okay? So g prime of x will be d dx of 6 to x root t cubed dt. All right, so this is going to be root x cubed. All right, but it does say integrate to find and then differentiate. So let's do what we're told. So g of x will equal then, so that's 3 over 2, right? So we're going to raise it, reciprocate it, analyze 6x. Okay. And we're going to get 2x to the 5 halves over 5 minus 2, 6 to the 5 halves over 5. Okay, we'll just leave it like that. This is, this new function here. And now let's g prime it. Well, 5 halves is going to come down. Multiply with the 2/5 x to the 5 halves minus 2 over 2. And that'll just be 0. Right, similarly here, and this is just going to equal, look at everything, if I differentiate this, g prime of x will equal d dx of, and you see that, inverse situation. This has to be just some number. I don't care if it's a million. I don't care if it's -2. It doesn't matter. This is going to be cosine of x. Okay, but let's go through it. So integrate it up. G of x is this integral, so let's do it. So this will be sine of t from 8 to x. So g of x will be sine of x minus sine of 8. G prime of x will be cosine of x minus 0. All right. So where will you find this useful? You'll find this useful. You're going to be so used to integrating and knowing your stuff and all that, and you might be thrown. You might get yourself in the weeds and be given something that you don't know what to do. Meaning you don't know how to integrate. And so just remember, if you don't know how to integrate, you don't know how to integrate, and that's fine. Look for another path. So let's say you're given that this function is the integral from 6 to x of this. All right, and then, if you're asked to find the derivative of this, and you're like, wait a minute, I gotta integrate it, I don't know how to integrate that, and instead of trying to make up your own math rules, we know that if we have to take the derivative of this, that puts the d dx here, those knock each other out, right? As long as that's just some number, and that's your new variable, then this is just x squared plus 4. So you might be thrown a problem where it looks really complicated and you try to do all this crazy stuff that you don't know how to do yet, and then you get your quiz or test back and you're like, oh my goodness, I could have just used the FTC. Okay? So even though we don't know how to find that antiderivative, we can find the derivative due to the fact that they're inverses. Okay? And then so same thing here. I don't know what to do with this. I have no clue what to do with this. And then we have this lower bound is, gosh, is that t? I can't even really read. Yeah, that's the variable, okay? And that's 2, okay? So this, FTC needs this to be a number and that to be the variable. So I don't know how to deal with that at all. I'm not equipped to deal with that. The integral of inverse tan, I don't know what to do with that. But look what I'm asked to find, the derivative. The derivative of an integral, those are inverses, so that is good news. And so what do I need? I need this to be a number, and I need this to be a variable. So let's make this integral uncomfortable. And when I make it uncomfortable, I just negate. Okay, and now, let's find g prime. That just plays knockout, and negatives in front, and we just get the new variable, which is that upper bound. That's it. All right, so this suggests FTC applies when the lower limit is a number, which I've been speaking to, and the upper limit is that new variable. All right, next page. So let's complicate it a bit, as always, okay? Find g of x and differentiate to find g prime of x. All right, so we're going to go through the process. Something looks different here. Something looks different. That's just a number, yay. So we're differentiating an integral, but that is not just x. So what is going to happen here? All right, so let's just go through the process. So let's integrate. All right, so g of x is this integral, so g of x then is sine of t, okay, g of x is sine of x squared minus sine of pi over 2, all right, so g prime of x is cosine of x squared times the chain. And, sine of this is just 1, so that's minus 0. And so g prime of x here is cosine of x squared times the chain. All right, so what happened there, right? If this upper limit is not just x, in comes chain rule. And you can see it unfolding just like that. Okay, same thing here. So g of x is this integral, so let's do 2 cubed over 3 minus g squared over 2 from 3 to x. Gosh, I can't even see that. What is that? Is it x cubed plus 2x, okay? So g of x is going to be x cubed plus 2x cubed over 3 minus x cubed plus 2x squared over 2 minus 27 over 9 minus 9 over 2. Okay, so let's differentiate that. So if I differentiate that, I'm going to get 3x cubed plus 2x squared over 3 times the chain. Okay, and minus 2x cubed plus 2x first, 2 times the chain. And that just will, it's constant, differentiate to 0. Okay, so what exactly happened here, right? What exactly happened here? If you were to look at all of this, you would see, if I took, you could factor out this chain. Let me see where I can have some room here. I'm going to write it down here. I hope that's okay. G prime of x. If I factored out the chain, and let's actually factor it out in the back. If I factored out this chain, I'd be left with x cubed plus 2x squared minus x cubed plus 2x. Okay, so let's think about that from the get-go. So from the get-go, if I had just dumped this upper bound in right there, I would get x cubed plus 2x squared. There you go. And if I had just dumped this here, I'd get minus x cubed plus 2x, and then the chain at the upper bound. So that's what's going to happen with this FTC, derivative of an integral, when your upper bound is not just x. Okay, so the FTC does not apply directly in 8 and 9 because the upper limit is not x, but it's a function of x. When we took the derivative of g of x, we had to apply the chain rule. Okay, so the following formula applies when the upper function, the upper limit is a function of x, not just x. I mean, I suppose x is a function of x, but something other than just x. So written like so. So when you do this, you just throw, you get f of that g of x. So this goes, the function goes in here, and then the chain. Okay, so we got this question. We got derivative of an integral. Great, those play knockout. Love it. Check the bottom, constant. Love it. Not just x. So slightly more work, but not bad. That's it. Sine of 25x squared times 5. Okay. Next one, 11 d dx of this. Okay, so let's see. Okay, this isn't good. I need this to go up. So let's make the integral, uncomfortable. And we'll put a negate sign. Arc sine t dt So constant function of x, okay? So this will be negative arc sine 1 over x times the chain, okay? And so the chain of 1 over x is x to the negative 1. Okay, so it's negative 1 over x squared. So I would probably write this as 1 over x squared arc sine of 1 over x. All right. All right, so here we go, more examples. 12, find DDS of cosine of x, top bound, negative 6 on the bottom, u4 to u. This looks great, right? New variable, that all looks good. So these need to match. It's just all good. This is set up perfectly. So I guess a couple of things to note is that this will be a variable and these two need to be the same. Otherwise it just doesn't work. It's not like defined correctly, if that makes sense. And I don't really think you'll run into many questions where it's not set up. I haven't seen many tricks in that area trying to fool students. So I think you'll be okay. But it's never a bad idea to just say, okay, I'm differentiating with respect to s. That's going to be my new, because this is going to become the new. So this and this needs to match because that's going to be the new. So after you do order of operations, you want to be differentiating with respect to s. It's all worked out great. So try not to overthink it. It's usually presented to you in that way. Anyway, so let's do DDS of u to the 5th over 5. Wait, I'm just going to use FDC. I'm so used to having to go through the process. I'm forgetting to use the gift that we are given here. All right, so this is just going to be cosine of x to the 4th power, and it's the new variable, which is s, okay, times the chain. All right, so what is the chain here? Differentiate cosine to negative sine of s. That's it, okay? All right, and so find the derivative of this integral. Great. And so now we're looking at one where the lower bound is x and the upper bound is x. So shoot, what do we do here? I don't know. I don't know what to do. Well, let's see what happens if we just go through it, the long way, and then we're going to formalize it here. Okay, so the difference in here is this is just a number. Difference here is now we have two functions. Okay, so let's just see what happens. All right, so u is going to be u cubed over 3. All right, and we're going to go 2x, 3x. All right, so we're going to get 3x quantity cubed over 3 minus 2x quantity cubed over 3. And then we're going to ddx that, right? So we're going to ddx that, and we're going to get 3 is going to come down. Okay, times the chain, minus 3 is going to come down, times the chain. All right, so what's our end result here? Our end result is going to be the following. 3x squared minus 2x squared. Quantity squared. So how does that compare to like FTC thinking? Okay, so let's say we dump 3x in there, 3x squared times the chain, and we dump 2x in there, 2x squared times the chain, and that's exactly what happens. All right, so if you're continuous and g and h are both different, so now the lower bound is a function and the upper bound, then you're just going to get, throw in the function here, the upper bound function, times the chain, and minus off times the chain. All right, so now I can approach this one and say, okay, I am taking the derivative of an integral. I have a function and a function, so the upper bound is just going to go in. Times the chain. Okay, so what is the chain of this is just 2 cosine. All right. Oh, no, sorry, chain of the upper bound. My bad. Chain of the upper bound. Okay. This is like my 5th video today, so. Chain of the upper bound, okay, and then minus ln of 1 plus 2 cosine of x, and not the chain of here, but the chain of the lower bound, which is negative sine of x. Negative sine of x, so I'm just going to do this. That's okay. So ln of natural log of 1 over 1 plus 2 sine of x plus cosine x plus ln 1 plus 2 cosine x sine of x. All right. So those are our notes for Monday. All right, guys. I'll continue 6.4 part 2 in another video. All right. See you guys.